All right. So we just took a test, didn't we? Yeah. Well, you'll get those tests back on Thursday, and we'll go over how to do those problems. But until then, we're going to be continuing on with the material. Let's see here. Tests over 1 and 2, 3 and 4. So 5 and 6 is what is up here. Actually, let me take a look at these contents. Come on, let's go. Let's go. Where's the contents here? There you go. I don't get this book. It's got more fish in it than a marine biology book, but it doesn't show me where the contents are. Here we go. Applications. Okay, so we went through that. So chapter 5 and 6 will be on our third test. And then our final will include chapter 7 and will be comprehensive, if that makes sense. So we'll have a third exam over chapters 5 and 6 prior to the final. On the final, we'll be tested over chapter 7 and the whole semester. It's comprehensive. So the final exam is worth 30% of your grade, whereas midterm exams are worth 25. So that extra 5% is for the extra comprehensive nature of the test. I will not speak about the exam, the one that we took, until on Thursday, and we'll talk about it then. We'll go over how to do the problems, and we'll see what happens. So after this, we're on chapter 5. And just like, well, I'll say one more thing. Just like how if the first test was too easy and I made the second test, let's say I made it too hard, I'll make the third test a little easier to even it out. Or if the grades are very bad, you'll get a curve or some sort like that. So what I want for you guys is to be focused on the learning. Okay? Focus on learning as much as possible. But at the same time, do not sit there and bank on some type of like curve or extra points helping you. Make sure you try and get it there based off of your own merits. But I may also include additional extra assignments that you can do that can help bump your points up on your exam too, because I didn't make that much harder than the first exam. We'll see what happens. I have not graded them yet. Just know I'm on your side. I want to see you guys do well. Okay. So this is section 5.1. So let's talk about some identities. All right. So let's review what we know so far. We know there's a sine of theta, there's a cosine of theta, and we know there's a tangent of theta. Furthermore, we know that there's a 1 over sine of theta, which is cosecant theta. We know that there's a 1 over cosine of theta, which is secant theta. And we know that there's a 1 over tangent of theta, which is a cotangent of theta. Next, we know that there exists Pythagorean identities, such that the sine squared of a theta plus the cosine squared of a theta gives you 1. Next, using this identity, you may rederive the other Pythagorean identities. Namely, that the cotangent squared theta is equal to, what was it, 1 plus cosecant squared theta. I believe this is it. I don't memorize, I just rederive. Is it cotangent? Yep. So yeah, cotangent squared theta is equal to cosecant squared theta minus 1. So, all right. And then, then secant, so then that's that one. And then tangent squared theta is going to equal secant squared theta minus 1. Those can be derived. Shall we derive one of them? All right, this is going to be like the doctor's office. I'll derive one of them for you. 1 or 2? 1 or 2? Someone just give me a 1 or 2. Pick one. 2. Thank you, Travis. Let's derive this one right here. All right. Tangent squared theta should equal secant squared theta minus 1. Let's write what secant squared theta minus 1 equals. Well, this is the same thing as 1 over cosine squared theta minus 1. But that's the same thing when I multiply both sides. When I multiply top and bottom here by fancy number 1 and combine under the same common denominator, we get 1 minus cosine squared theta over cosine squared theta, right? Oh, but 1 minus cosine squared theta is the same thing as sine squared theta. Why is that? Well, I just said 1 minus cosine squared theta is equal to sine squared theta. All I got to do is subtract the cosine squared theta from this equation, and I get sine squared theta is equal to 1 minus cosine squared theta. So yes, these identities require you to assume this initial identity. The initial identity I've proven already in the past. It's a consequence of the Pythagorean theorem. I'll do it again if you want. So you have a unit circle, so you have an arbitrary theta. It has an x and a y, but that equals your cosine of theta and your sine of theta. Okay. By definition, if you exist on a unit circle, this is true because of the Pythagorean theorem. A squared plus b squared is equal to c squared. This is a unit circle, so any line emanating out of the origin and intercepting the arc of the circle has distance 1, has length 1. Electronic devices should not be out right now. Okay, so then notice that if I replace it with cosine and sine, I get this becomes cosine squared theta plus sine squared theta is equal to 1. And thus you get this. And utilizing this, because x is equal to cosine of theta and y is equal to sine of theta, that's why I'm replacing x squared with cosine squared. I'm replacing y squared with sine squared. Okay. So that's why that's happening. Then over here, we utilize that in this numerator to get this. We're trying to show that secant squared theta minus 1 is equal to tangent squared theta. And we've done it because this is the same thing as tangent squared theta. Because sine over cosine is tangent. So sine squared over cosine squared is tangent squared. All right. So there's this identity, there's this identity. You could have easily proven the second one, or you could have easily proven this. We proved that. We could do them really quickly. What else is there? Yes, the fact that there's symmetry. That sine of negative theta, because sine is an odd function, this minus can pop out of theta out in front. Because sine is odd, this is an odd property function. And I showed you geometrically why it's odd and numerically. What about cosine? Cosine eats that negative because it's a what kind of function? Yes, ma'am. It's an even function. So what is tangent? What does it equal? Is it tangent even or odd? You don't know, huh? Well, we can test it. Well, what is the tangent of a negative theta really equal to? Well, it equals, by definition, the sine of a negative theta over the cosine of a negative theta, right? By definition, that's true. Then over here, we know that sine is odd and cosine is even. So in the top, that negative pops right out. And at the bottom, it eats that negative. But what we have up there to our far right is the same thing as negative tangent of theta with the negative out in front.
Would it be odd or even?
You tell me. If the negative was inside and it pops right out, the negative was inside and it pops right out, which one does it look? Does it look more even or does it look more odd?
Odd.
Yes. Tangent is an odd function. So we've discovered that this is what happens with tangent. This is all stuff we've already covered. Okay. So now let us verify some identities out here. So how about 1 minus tangent quantity squared? We'll say that this equals secant squared plus 2 secant squared theta plus 2 tangent of negative theta. Let us prove this result. Okay. I'm going to start off with the left-hand side. And I'm going to rewrite it like so, because that's what it really is. Then we distribute or FOIL, if you will, to get 1 minus 2 tangent theta plus tangent squared theta. Right? Our tangent squared theta is how we're going to arrive with that secant squared stuff. Because remember the identity that secant squared theta was equal to tangent squared theta minus 1. I mean plus 1. I mean plus 1 here. There we go. Secant squared theta is equal to tangent squared theta plus 1. So that means this tangent squared theta, if I solve for it in this equation, it's secant squared minus 1. So I can directly replace this with secant squared theta minus 1. Plus this 1 minus this 2 tangent of theta. So then you will notice that the 1's cancel. So what remains is a secant squared theta minus a 2 tangent theta. But that is not what we wanted. We wanted secant squared theta plus 2 tangent of negative theta. You don't have that. Man, let's just quit. Anybody got any suggestions? Because I'm about to quit.
Well, secant squared theta minus 1 equals tangent squared theta, right?
Yes. That doesn't help us out here, because the problem here is that you have a minus here and a plus here, and then a minus here and a plus here. Just utilize the fact that tangent is an odd function right here. Meaning that if there's a negative out in front of it, the negative can go out in front of what's inside the parentheses.
So you can just switch it?
Yes, sir. You are correct. And we've proven that you can just switch it.
Even with the 2 right in front of it, like that doesn't change anything?
Nope, the 2 out in front of it doesn't change anything. And here's why. I can multiply this equation both sides by a 2. Right? Multiply both sides of this equation by 2. It's still true. Voila. We've proven it. Quod erat demonstratum. It's this thing that mathematicians say after we prove stuff in Latin. It means thus it has been shown, or thus it has been demonstrated, or thus it has been proven.
That's it.
Yep. Moving on to the next one. Sine squared theta, tangent squared theta. Sine squared theta, tangent squared theta is equal to tangent squared theta minus sine squared theta. Let's prove this result. I'm going to start off on the right-hand side. What does this equal? Well, tangent is sine over cosine. So tangent squared is sine squared over cosine squared. And this is divided by 1. So for us to establish a common denominator, I have to multiply top and bottom here by cosine squared theta. And after I do that, I will put everything under the same denominator. And we would get we hope to establish this as a product between sine squared theta and tangent squared theta. I can already see a tangent squared theta in our lives if we do what to the numerator?
I have a question.
Yes, sir.
Did you cross multiply the cosine with the negative sine squared?
No, I did not. I'll tell you what I did here. Thank you for asking.
I just got confused.
That's okay. You're not the only one who's wondering it. So, as I said before, what I did was I multiplied top and bottom here by a fancy number 1 to establish a common. So then that ends up equaling.
Okay. That makes a lot of sense.
So once I got that, I just put everything under the common denominator to save writing.
Wait, I see it. Thank you, sir.
Does that make sense?
Yes, sir. Thanks.
All
I
right.
appreciate that.
No problem. Thank you for asking. So that's how we get to here. There's something I could do to this numerator, though, for us to make it look like this, or at least get one step closer to making it look like that.
Could we separate it so it'd be sine squared theta over cosine squared theta minus sine squared theta times cosine squared theta over cosine?
Yeah, but that would just be undoing what we're doing,
Oh, okay.
right? Good idea, though. Good idea, though. Do you guys see a common term in the numerator in each of the?
Sine. Oh, take it as sine.
Yeah, take out a sine squared theta. Factor out a sine squared theta. What happens now is I get a 1 minus cosine squared theta in the numerator. The denominator retains this cosine squared theta because we weren't doing anything to it at all. It just moves along for the ride. Notice that sine squared theta over cosine squared theta is equal to tangent squared theta. Times this 1 minus cosine squared theta business. And I already know we're done. This is the penultimate step towards completion of the proof. What is 1 minus cosine squared theta really? And why?
It's equals sine because
Sine squared theta, right?
yes, sorry, sine
Mhm.
sine squared theta because sine squared theta plus cosine squared theta equals 1. So you just subtract one of them to isolate the sine squared theta.
Yes. So we get this chunk and we placed it right here. Boom. Oh, and that's what we were trying to show. Mathematicians also like to make a box like that when we're done proving stuff. Why? I don't know. you got to have some, like, celebration you do once you do something. So like in soccer, Cristiano Ronaldo goes like, shoo, and in football, they have their own kind of celebrations, when you score a touchdown or make a basket. This is our celebratory symbol. Let us have some fun with it. We've completed the proof here. Let's move on to the next proof, unless anybody has any questions.
Does it matter if you put like the tangent squared in front of the sine squared, or no? Like for the final answer?
Yeah, that's a wonderful question. Yes, the answer does not matter. And here is why. Let me ask you a question. What is 3 times 4?
12.
Okay. What is 4 times 3?
12.
Why the order doesn't matter. Because when you evaluate sine squared theta, tangent squared theta, for a theta, they output real numbers. And real numbers, when you multiply them, the order doesn't matter. That is when you exist in a commutative field with unity. There is mathematics in which the order does matter. Furthermore, we have not invented the appropriate mathematics to understand what it's like to fall into the infinite curved region of a space-time that is near the event horizon of a black hole. So it could possibly be that inside a black hole, that space and time does not commute like so. So that 4 times 3 does not equal 3 times 4. Well, what I'm saying is that our assumption that this is true is only true for us, like here. Near a black hole and inside a black hole, mathematics as we know it can be completely different. We have not discovered the mathematics, the appropriate mathematics. We take this on good faith. And it's been working for us so far. But it is naive, if you will. And it's only an appropriate assumption in certain situations. Our situation is an appropriate situation. But isn't that cool? Yeah, this mathematics we're doing here is just the tip of the iceberg of knowledge and truth, mathematical knowledge and truth. We're only scratching the surface here. What about cosine of theta over 1 plus secant? What about when this equals 1 minus cosine over tangent squared? How do we prove this guy?
It's cosine squared theta.
Oh, yeah. No, it's just a cosine of theta. It's just the theta started looking like a 2. I need to go back to writing with my left.
But the tangent squared theta is so small.
Yes, ma'am. Yes, ma'am.
You start with the right hand side, right?
If you want, doesn't matter to me. We'll start with the right hand side to honor Pam's request. All right. We want to somehow make this to look like cosine theta over 1 plus secant theta. So how are we going to pull this off here? Any suggestions?
Undo the tangent squared theta, which is sine squared theta over cosine squared theta.
This was one of our identities, was it not? So why did I think to do this? Well, first of all, we can't actually you know, so look over here. We started on the right-hand side, did we not? Our goal is go to the left-hand side, right here. So we notice that in the denominator on the left-hand side, there's some secants.
Mhm.
So that's when you might want to think, okay, we might want to use this, but it may or may not be immediately useful. Right? We could replace tangent squared theta with that. Or we could try what you're saying and replace it with sine over cosine. There is multiple ways of doing this. So to honor your suggestion, let's see if your way works.
You're not really-
Yeah, exactly. We're going to try. So doing that and multiplying by reciprocals, I get 1 minus cosine squared theta. It was over 1 multiplied by reciprocals is this. But now look, when we multiply it through, we're getting some cosine squared theta terms, and we're getting a cosine cubed term over here. Right? And if I were to distribute that to both, I'd be getting a tangent in the numerator, and that's not what we want. What we want is a cosine in the numerator, right?
Mhm.
See what I'm saying? If I were to, actually, we'd get a cotangent, right? This would lead to a cotangent. There's not much to work with in that situation. So this method of doing it leads us to what seems like a non-obvious way to progress with the proof. So this is how doing these problems are. You try a way and you see where it gets you. If it got you to the proof, good. If it didn't, good. You try a different way. So just replacing tangent squared theta with sine squared theta over cosine squared theta did not work. So how about we try this? This substitution has promise because it will introduce a secant in the denominator and it will keep this cosine in the numerator. Tangent squared theta is the same thing as secant squared theta minus 1. Okay. But then we notice that this is the same thing as 1 minus cosine of theta divided by 1 over cosine squared theta minus 1. Then we notice that this is the same thing as 1 minus cosine squared theta divided by 1 minus cosine squared theta all over cosine squared theta. When you multiply top and bottom here by cosine squared theta and regroup. Then we notice that when we multiply by reciprocals, this ends up giving me cosine squared theta, and this ends up giving me 1 minus cosine squared theta. So then we notice that now we have cosine squared theta times 1 minus cosine of theta. Everything divided by 1 minus cosine squared theta. Interestingly enough, let us analyze what 1 minus cosine squared theta could equal. So yes, of course it can equal, of course it could equal sine squared theta, right? But would that be useful? Do we want cotangents in what we have here? No. So this is not necessarily the right thing to pick. Another way to think about it is that 1 minus cosine squared theta, can I represent this as a product of two factors? Why, yes. Right? If I multiply this times that, they'll give me that negative cosine squared theta. And what will give me a positive 1? Is that so? Okay, so this becomes negative cosine squared theta plus cosine theta minus cosine theta plus 1, right? Negative cosine squared theta plus cosine theta minus cosine theta plus 1. So the middle terms cancel. So I get that negative cosine squared theta plus 1. Aha! I can factor this 1 minus cosine squared theta into this product right here. Why is that useful? While you're thinking about why is it useful, I'll rewrite this. Okay, guys, let me give you a little word to the whys. Why was I able to come up with this so quick? It's because I've practiced this a lot. If this was not immediate to you, that is okay. It requires practice, and you can achieve that. I guarantee you. With practice, you can think about that as well. It's just knowing how to factor this. It's almost equivalent to knowing how to factor this polynomial in x, right? Remember how you could factor polynomials? Yeah. So it just takes practice. Do not be discouraged if it doesn't make immediate sense to you. It's going to take practice for it to make sense to you. So notice I can rearrange this cosine of theta to say this is 1 minus cosine of theta. Because as we have discussed, the order doesn't matter. As Joshua asked, the order doesn't matter. Notice that we have a common term here and a common term here. They're the same thing in the parentheses. So we can cancel the whole thing out. So I get cosine squared theta over cosine theta plus 1 over here. But I want to seek it in that denominator, and I don't want a cosine squared in the top. Aha! I know what that means. That means I need to multiply top and bottom by a 1 over cosine of theta. Say what? Say what? Well, I thought of that idea because I know I need to make this into a cosine of theta. So if I divide it by a cosine of theta, it won't be a cosine squared theta anymore. It'll just be a cosine of theta. Exactly what I want. Furthermore, I know if I distribute that 1 over cosine of theta to each of these terms here, that over here, it would remain a 1 over cosine of theta, which would turn into a secant theta. And over here, it would just be a cosine of theta over a cosine of theta, which would just be a 1. Precisely what we want. And it is okay if this doesn't click right away. It requires practice. Just like who popped out the womb knowing how to ride a bike? Which one of you guys popped out the womb knowing how to ride a bicycle? But who here can ride a bicycle? Almost everybody in here. Can you not ride a bicycle? You can ride a bicycle. Everybody in here can ride a bicycle. But did you pop out the womb knowing how to do it? No. You fell and it hurt and you scraped your shoulder and your knees, and then you tried again and you tried again and you tried again, and then you eventually learned. This is the same thing. It's going to require some pain. It's going to require some pain. Just know when your brain hurts, when you're confused, that's your brain getting stronger. When your brain is hurting, that means your brain is getting stronger. So over here, let's perform this operation that I've indicated. So then notice that when I multiply here, I get a cosine of theta. When I multiply here, I get a cosine of theta over cosine of theta plus a 1 over cosine of theta. This reduces to 1. This reduces to a secant theta. And you're done. And we can get away with it too, because multiplying anything like so is like identically multiplying times a -1. Anything divided by itself is positive 1. Anything divided by itself is a 1. So we can get away with saying this whole expression equals this expression, which equals this expression. Equality holds. And we're done with the proof. Oh, it seems like, okay. Did you guys get my email about the number of class periods we have left? Did you guys read your emails?
Yeah.
Okay, good. Did you guys get that email about me updating the syllabus? How we're ahead of schedule? And yeah, during finals week, those may be optional class periods.
Oh, yeah.
That's still a thing?
It's still a thing. I'm checking forward. I'm trying to forge forward and make that possible for you guys. I believe that would be really good, right? That way you can show up to class and get optional review for the final if you want. And if you don't want, you could just sleep in and focus on other assignments. But you still have to take this final. You know, you're not forced to show up. SNU is one of those institutions that kind of forces your attendance. Not all institutions do that, right? But this institution does penalize you for lack of attendance. So I will count everyone present, even if you don't show up on those days. How about that? I'm telling you, it's not empty words. I really am on your side. I want to see all of you successful. The ball is in your court. You have to work hard. I'm working hard. So I want you guys to also work hard. So let's prove another one. Secant of x over sine of x is equal to minus sine of x over secant x. Tangent squared minus tangent squared plus cosine squared over tangent squared. All right, cosine squared. Yeah, over tangent squared x, or just tangent x. Okay, I need to make sure I wrote that right. Secant over sine minus sine over secant, a dyslexic's nightmare, is equal to tangent squared plus cosine squared over tangent. All right, we're in business.
So is x taking the place of theta?
Yeah.
Okay, so it's still like a degree?
Oh yeah.
Okay.
We could have had t's. We could have had thetas. We could have had phi's. It doesn't matter. It's a placeholder. Okay. So I'm going to start off on the left-hand side. We want to get this tangent squared x plus cosine squared x over tangent x. Okay. So far, we're adding two fractions that don't have a common denominator, or subtracting two fractions that don't have a common denominator. So I have to multiply top and bottom here by something to establish a common denominator, right? Namely, this thing desires a sine, so, and this term desires a secant. So what do we get here? We get secant squared x all over secant x sine x minus sine squared x over secant x sine x. Okay. You can just write them all in the same denominator. Sometimes when I skip that step, students get lost, but that is a step that you need to get used to. I'll point it out explicitly here. So now, don't expect me to do it explicitly all the time. So now we have this. This is some good news, because that denominator is tangent.
Oh,
The denominator is tangent. Why is that so?
because secant is 1 over cosine. And it's been multiplied.
Absolutely. That's why. And sine over cosine is tangent. Now, secant squared minus sine squared. What is going on? How can we turn that into a tangent squared plus a cosine squared? Well, one thing we do know is we can unpack the definition of secant squared. Can we not? Right? So now, again, we need to establish a common denominator because the sine squared is divided by 1. So we'll multiply top and bottom by cosine squared theta and put them under the same denominator to get 1 minus So now we got to multiply by reciprocals. And then I'm going to erase all the work we've done to that point. I guess I'll let this remain so you can copy it or whatever. All right. So then taking this, bring that equation over here. So then I get 1 minus sine squared x cosine squared x divided by tangent of x cosine squared x. Doo-doo-doo. Seems like we're not getting anywhere. Seems like we're not getting anywhere. But we are. We want a tangent in the denominator, not this. And we want this one to be a tangent squared x plus a cosine squared x. But if we want to keep that tangent in the denominator, why don't we pull out a cosine squared x from the numerator? Factor it out. Because now I can cancel them out. This is a tangent, it's not a plus.
How did that become 1 over cosine squared x?
Because, good question. That is what it has to be, because when I factor out by a term, it must be such that when I redistribute the term, I restore the original equation. Notice that the only way I can factor out a cosine squared x out of the term 1 and sine squared x cosine squared x is that I remove a cosine from here, just leaving the sine squared x over here. And this 1 has to become a 1 over cosine squared x, because when I distribute this cosine squared x, it should restore the 1, and it should restore the sine squared x cosine squared x.
Okay.
Afterwards, it'll cancel with the denominator. So now our denominator is beautifully just tangent of x. And our top, when I multiply top and bottom of this term by cosine squared x, I get 1 minus sine squared x cosine squared x, everything divided by cosine squared x. All right, notice that when I distribute what happens?
Wait.
Okay. Okay. Give me a second. I'll unconfuse you. over here, so we cancel out the cosine squareds, so we get this.
How does that turn out to be? Oh, well, we have to find out a common denominator. Okay.
Yeah, so I'll just write it step by step. So this becomes 1 over cosine squared of x minus sine squared of x. Everything divided by tangent of x. Notice what does this imply? This implies that right? But is that useful? I don't know. So over here, this would become a secant squared x, but that's not what we want in the numerator. We want that cosine squared x plus that tangent squared x. What does tangent squared x plus cosine squared x really mean? What does this really mean? How do we know that we've established what we want? Really, it's sine squared x over cosine squared x plus cosine squared x. But that's really the same thing when I multiply top and bottom by cosine squared x on this right term. I get sine squared x plus cosine to the 4th x all over cosine squared x. That's the numerator here. That's the numerator here. So if we can turn because our denominator is already tangent x, it's good. If we can somehow turn that numerator into a sine squared x plus cosine to the 4th x over cosine squared x, we'd be good. So let us now then perform this operation, establishing a common denominator. This is the step that confused you guys, right? Let's establish a common denominator, and we know we're working towards this in the numerator, in the yellow. 1 minus sine squared x, cosine squared x divided by tangent of x. What am I saying? I totally neglected one of those terms. This is 1 minus sine squared x, cosine squared x. Everything divided by cosine squared x divided by tangent of x. We really want a sine squared x plus a cosine to the 4th x in the numerator here, right here. Well, we got a 1 minus sine squared business. Could it be possible that we could replace using something like this? Maybe not necessarily that one, but how about we say sine squared of x is equal to 1 minus cosine squared x. Why would we do that? Well, it's because that will allow us to multiply that cosine squared times another cosine squared to get us that desired cosine to the 4th. really short on space on this one. So I'll keep that in the yellow. Okay, so working from right to left, we will have that this is 1 minus the quantity cosine squared x minus cosine to the 4th x all over cosine squared x all over tangent of x. Distributing that minus, I get this is 1 minus cosine squared x plus cosine to the 4th x divided by cosine squared x divided by tangent of x. That's pretty good because we have that cosine to the 4th x. All we need is that plus sine squared x, right? Oh, but voila. Voila. Notice that 1 minus cosine squared x is the same thing as I already have it here in this box. And we are almost done. One last step here. So bring the calculation over here. Let us delete this info. Then I'm going to distribute this cosine squared to both these terms here. So I get sine squared x over cosine squared x plus cosine to the 4th x over cosine squared x. But everything was already over tangent. Okay. Now this left term becomes tangent squared x this right term becomes cosine squared x because cosine to the 4th over cosine squared cancels out 2 of them. And this is all over tangent. We started off with this. We worked our way, we worked our way, we worked our way all the way to this. And it requires practice. And it requires fluidity with the equations, meaning you need to quickly recognize, oh, if I have for instance, if I have a 1 minus sine squared, that has to be a cosine squared. You know, you need to have fluidity with those substitutions. So how do we show something is not true? We got good at showing things that are true. We just got good at showing proofs here. How do we show things that are not true? So like, for instance, sine of 2x is equal to 2 sine of x. Is this true? I'll tell you one thing. This is true.
I mean, if we were to come up with a value for x and then just solve, it would give us different results, right?
Yes. Give me a value for x.
5.
How about with like pi is involved?
Oh.
How about pi? Okay. Dun, dun, dun. Let's have them battle. Sine of 2x versus 2 sine of x. X equals pi. What do we get? We get sine of 2 pi over here. And then we get 2 sine of pi over here. But what is sine of pi? But what is sine of 2 pi? Wait a second, Pam. They agree. What's going on here? If they agree, then this equation should be actually whole. See, the truth is, it doesn't matter if this equation is true for some x. It only matters if the equation is true for all x. So all we have to find is an x that does not establish this equality. We have not found it yet. So let's search even further. How about pi over 2? Then I get sine of 2 times pi over 2 over here. And I get 2 sine of pi over 2 over here. Over here, this is 2 times a 1. This is a 2. Over here, this becomes sine of pi, which would be, no, it's 0. Aha! Now, 0 and 2 are not the same. Beautiful. So we found a counterexample. So we've disproved. That's not true. So that's one way you can show things are not true. So, okay, show that sine of x does not equal cosine of x. Show. I can say show that it does not equal, or I can say either way. This one doesn't give you the hints that they don't equal. But how would you prove whether this is true or not? Or how would you prove that it is not true? You'd pick an x in which the output for this is different for the output of that. What about x is equal to 0? Well, that would imply sine of 0 is equal to cosine of 0. Well, cosine of 0 is 1, sine of 0 is 0. 0 doesn't equal 1. For those of you who weren't here earlier, I was discussing our last test that we just took. I'll give those tests back to you on Thursday, and we'll go over how to do those problems then. I did make that test more difficult than the first, and I recognize that. So let's see how the scores are, and if they're not as flattering as the first round of exams, well, I'll do some stuff to help you guys out. I'll give you some extra credit opportunities that will put some bonus points on your test. And then I'll probably make the third test not as difficult as I did the second test, maybe. Or maybe I might add more bonus points. Either way, I'll figure out how to help you guys out and kind of even it all out. I didn't make a mistake. That's definitely not true. I didn't ask you anything that you weren't exposed to in class. But at the same time, I don't want to tank your grades because you guys are working very hard in here, and you don't deserve to have. You deserve to get the grade that you've been working for. That's all. So that's all I'm saying. So don't worry if some weird stuff's happening with that. I'll make sure to, if it needs it, put a curve on that test. because I did make it much more difficult than the first. So yeah, I can't guarantee you what that numerical value of the curve will be. It'll just be something appropriate to create a normal distribution of grades. That's everything in class for today. If you guys have any homework, you can let me have it. I'll let you guys out 2 minutes early.
Hey, Professor,
Yes, sir.
did you get my email?
Yes, I did. About various emails. I have not been able to answer any emails.
No, it's okay. It's okay. I
But
was
I
just
did
gonna,
get it.
I just need some more like work with Unit 3 because that's what I've been
Okay.
struggling.
Okay, okay. All right.
I've tried. I just like I'm having a hard time getting it.
Okay. Have you checked out my YouTube channel?
I was not aware you had a YouTube channel. I was not aware you had a YouTube channel. What is
Oh
it?
yeah, I got like 1,400 subscribers. I'm a big deal, man.
Oh
I got
man.
how-to math tutorial videos on there. I'm not a big deal. I'm just kidding. But yeah. Oh, Harrison, you said you have time to take your exam?
When? Like right now?
Yeah.
I found it.
I have like homework. I mean, how long do you think it's gonna take?
It takes a normal class period in length. And you need to take that
Yeah.
before Thursday.
Before Thursday?
Yes.
Let's do it now.
You can do it now, yes. Okay. All right. So check out that YouTube channel. That should help you out. We won't be taking it here. We'll be doing it in the math office. Yeah.